Thank you. So, good morning, good afternoon, good evening, depending on where you are joining us today. So, welcome to the Harvard MIT Pre-Summit webinar series. This is a lead up, a crucial lead up to the Global Health Catalyst Summit. So, my name is Stephen Avery. I'm a professor of radiation oncology, director of global radiation physics at the University of Pennsylvania. And I am honored to serve as your moderator for today's discussion about transforming on the oncology workforce, the development of that. So this webinar series is designed to set the stage for critical conversations that we can facilitate collaboration and knowledge exchange among experts, innovators, and leaders in global health. So today we focus on a particular pressing challenge. How do we train and equip the oncology workforce of the future to meet the growing burden of cancer worldwide? So today we will explore under the current challenges in global oncology education, particularly in low resource settings, how emerging technologies such as artificial intelligence, virtual reality, the use of holograms can be leveraged to enhance training and workforce capacity, and what innovative models and global partnerships are needed to build a well-trained oncology workforce. So we have an esteemed panel of experts with us today who will share their insights and experiences. Before we begin our discussion, I have a message from May Abdel Wahab, who's director of the IAEA Division for Human Health. And then I will invite each of the panelists to introduce themselves and share a brief opening statement. So with that, let me play the message from May.
Distinguished colleagues, dear friends.
Yeah, sorry.
Distinguished colleagues, dear friends. As director.
Try to get the show. Apologies for technical issues. Here we go.
Distinguished colleagues, dear friends. As director of the IA's Division of Human Health, I want to extend my heartfelt appreciation to the Global Health Catalyst Summit and organizers, and to Harvard and MIT in particular, for this exciting event. While I regrettably cannot join you for today's panel discussion due to a prior commitment, I'm excited about this effort, and thank you for the opportunity to share a few thoughts about such an important endeavor. As all of us are well aware, cancer care continues to remain a global challenge, despite the collective efforts we've made and the improvements we've seen. Data from the IAEA's Directory of Radiotherapy Centers, or DRAC, the world's most comprehensive database on radiotherapy resources, notably showed that in 2022, only 20.9% of all countries met the minimum radiotherapy resource requirement. This data, in turn, enabled the World Intellectual Property Organization to reveal an alarming trend through its 2023 Global Innovation Index. Cancer cases requiring radiotherapy are outpacing the available technology. The 2024 Lancet Oncology Commission on Radiotherapy and Theranostics elaborates on some of the disparities that persist, with low-income countries on average needing 8 times the number of currently available machines just to meet the target of 1 machine per 500 patients. Of course, equipment alone will not close the gap. We need adequately trained and credentialed medical professionals. That same Lancet Oncology Commission showed that our workforce in 2022 has to expand by more than 60% just to meet the cancer burden of 2050, with approximately 40% of this workforce predicted to be in upper middle income countries and nearly 25% in lower middle income countries. We need to develop context-sensitive solutions that can accelerate both the speed and scale of progress. Furthermore, the pending retirement on the horizon of the baby boomers and the increasing loss of professionals to non-clinical endeavors are additional strains. Under the current training standards, it has become evident that if we continue to require the same ratio of staff to residents and the 4 to 5 years of training for, let's say, radiation oncologists, the nominal level of staffing will not be achieved in LMICs. So a better and more efficient way to train is needed. The availability of complementary new technologies, such as virtual reality, augmented reality, holograms, digital twins, and the use of artificial intelligence and machine learning are but some of the creative tools and methods that offer promise and potential. The IAA has explored the use of some of these complementary tools, and the preliminary efficacy in terms of learning was noted. My colleague, Mauro Carrera, who leads the Medical Physics and Dosimetry section in my division, will kindly also share some information about current challenges in global oncology education, leveraging technology to bridge gaps, and building the oncology workforce of the future. In that vein, the Global Health Catalyst Summit, this pre-summit series, and today's topic in particular, are timely initiatives to spark innovation, ignite action, and cement collaboration on the very foundations of any high-quality cancer facility, its staff. On that note, I wish you all a fruitful and productive discussion, and thank you again for allowing me to provide these welcome remarks.
Thank you. So with that, why don't we just start from what I see on my screen. I see Andrew and then Mauro and then Claire with your just opening remarks that you have. And I think everyone should have the ability to screen share if needed.
So, Mauro going first? Or
you can go first, Andrew. Yeah, I'm just going from my screen. What I see.
All right, absolutely. Let me just share my screen here. Okay, hopefully you guys can see my screen now.
Yeah, it's coming. There it is. We see it.
All right. Good morning, everyone. And thank you very much for attending today. It's just... All right, so just a brief background about myself. I did my PhD at the University of Toronto more than 30 years ago. And then, and during my PhD, I developed the first digital mammography system. This is back when mammography was entirely in film screen. And since that time, I've continued to work in digital mammography. And in fact, what you see there on the screen is our latest digital tomosynthesis prototype that we've developed at the University of Pennsylvania. And this system is unique in the fact that it has an integrated PET system so that we can do PET DBT, much like you would do PET CT. And the reason for our success is that we developed more than 20 years ago the concept of virtual clinical trials. When GPUs were in their infancy in the mid-2000s, we started using them to do detailed microsimulation studies of imaging, where we would simulate the anatomy, we would simulate the equipment, we would simulate the display of the images, and we would also simulate the interpretation of the images. And this gave us an advantage against other labs and against industry, because to be honest, my biggest competitor are actually companies, GE, Hologic, Siemens, the people that are developing mammography systems today. And clearly they have far more money than a single university lab. And the trick for us was to make the design process cost effective. And we did that through these virtual clinical trials. In terms of education, I'm director of the graduate program in biomedical imaging and information sciences at the University of Pennsylvania. This is funded by a federal training grant. I'm also the editor and author, and one of the authors for the Diagnostic Physics Handbook from the IAEA. I was asked about 15 years ago to initiate an effort in creating this textbook. And we were very fortunate to have, a wonderful group of people collaborate to create this. And I know now we are actually working on the next version, the second edition of this book. And if you're not familiar with it, I think you should be. But if you're not, you should download it for free. And there are oncology, physics, nuclear medicine, and radiation biology books that complement it. So our graduate program at Penn, the Interfaces program, the idea was to train medical physicists to be equally fluent in the language of medicine and engineering or physics. And the way we did that was to actually have them attend the medical school, the didactic portion of medical school. So we typically have 3 students a year. Our 3 students are sitting in the medical school learning medicine with their MD colleagues. And in the afternoons, when the MDs go off to learn how to be physicians, how to elicit measure a pulse, elicit a reflex, things like that. Our students are in the engineering school doing engineering courses and engineering labs. And so we get them into the hospital first year, working with the equipment, doing experiments, learning the latest techniques, but also doing things like the gross anatomy lab. So they learn anatomy the way MDs learn anatomy. They autopsy a cadaver, and they learn medicine far more intensely than any of our other students. And since we're talking about new methods, these techniques are advancing. So, for example, holographic and computer simulation of anatomy is becoming a greater and greater part of that education. Where do I see medical physics going, or where do I think it needs to go? I think it needs to be more cross-disciplinary. And I don't think we can just add more courses. I think we need to rethink the way medical physics is done. So promoting physics minors for those who are in other programs, computer science, engineering, mathematics, things like that. That's how I was trained. I was a computer science with a minor in physics, and that got me into medical physics. Developing more dedicated undergraduate medical physics programs so that a lot of the base knowledge of the physics is taught during undergrad, and that allows grad school to be more specialized. And also it would allow a population of people that would come out of undergrad with an ability to impact medicine directly, so that grad school would not be necessary for all medical physicists. Expanding summer programs, the Penn Supers program that Dr. Avery did is a keen example of that. And really developing new methods to emphasize cross-training and cross-disciplinary teaching. And I think the end result will be positioning physicists that will be leaders for change in medicine. And I think that's really where we need to go. So at this point, I'll stop sharing, and thank you for the opportunity to introduce myself.
Thank you, Andrew. Mauro, would you like to have your opening remarks?
Yes, thank you, Stephen, and thank you very much for inviting us. I will give a short introduction, as May already introduced herself, and actually I'm the section head of the dosimetry and medical radiation physics section here at the IAEA, and as many of you might know, we are involved in several initiatives in capacity building and education, particularly in LMICs. As background, I am a medical physicist. I have been working for more than 20 years in a comprehensive cancer center in Italy, and I was a professor, associate professor for several university courses, and in particular, I served also the ICTP Master in Medical Physics course in Trieste, which is a course which is specifically aimed to train medical physicists from LMICs who do not have access in their country through training programs. And in the first 10 years, more than 200 medical physicists have been trained so far. And now as IAEA, we are, I'm serving this program from a different perspective, as we are scientific advisors to this program. And that's it. I'm looking forward to the discussion today. Thank you, Stephen.
Thank you, Mauro. And Claire, will you please share your opening remarks?
Yeah, thank you, Stephen, and thank you for the invitation to join today. I feel very humbled to be in such an esteemed group. I've just got a couple of quick slides just to introduce myself. So I'm a medical physicist also, currently based in Australia. So I work in one of the largest hospitals in New South Wales, the Calvary Mater Hospital in Newcastle, just north of Sydney, as a principal medical physicist in radiation oncology. I also have conjoint appointment at the School of Health Sciences for the University of Newcastle. So at the university, I teach into the RTT degree program, as well as the physics degree program, and also do physics training to radiation oncology residents. And then I also have an affiliate appointment at the Department of Radiation Oncology at the University of Washington, where I do some collaborative work in the global health space and education as well. One of my other roles is director of the ACP SEM Medical Physics Residency Program. So in Australia and New Zealand, our residency program is a multinational program. So we currently have 75 residents across 40 different clinics from the two countries participating. So it's a universal educational platform where all of our residents are assessed externally and monitored from outside of the clinics. So it's quite a collaborative learning process for our residents in those two countries. So I'm quite used to large scale and often remote learning, given the size of Australia and the remoteness of some of our clinics. In the global health space, I'm on the board of directors for the International Medical Physics Certification Board, which does fabulous work in terms of trying to raise the standard and improve the consistency and quality of medical physics training and professional practice internationally. I work as a consultant for the Nigerian Association of Medical Physicists, working with the Clinical Certification Board, and we're just introducing the first national medical physics certification in that country. So that's quite exciting. There's been a lot of work put into that over the last few years. I work very closely with Rayos Contra Cancer as an educator and advisor for the programs that they run. So they run very large scale online remote training programs and have been doing so for 6 years now. And then I'm also on the executive for the Asia Pacific and Ukraine Support for Better Healthcare Technology Foundation, which is based in Australia. And obviously Asia Pacific is our closest neighbour and actually have a lot of needs, both technological and educational. So where our aim is to support, I guess, our nearest neighbours first, and then also try and project that into a larger international space. So yeah, I'm looking forward to a discussion today.
Yeah, thank you, Claire. So I know that each of you have a background in medical physics, but I know also each of you work with physicians, therapists, nurses, the range of healthcare workers. So I think the conversation will be really addressed to the spectrum of health professionals in cancer care. So for our audience, if you have questions, please put them into the chat or in the Q&A, and then we will answer them. I have a couple of direct questions I have for our panel, and then we will go to the Q&A for the audience questions. So Claire, while we stop with you, let's start with you. I know that you successfully have run a residency program, online residency program. which is very impressive. So with the Global Oncology University, which basically is, the idea is that to have kind of an online degree program that we can offer. And so global partnerships like that are, increasing really to address gaps, and we see like these gaps may increase in the future. So what role do such initiatives play in shaping the future of oncology education?
Oh, look, I think that's a really great question. And certainly, you mentioned collaboration, and I think that's actually one of the key components to successful upskilling and training of radiation oncology workforces globally. So there are so many different groups of people doing fabulous work. The IAEA does amazing stuff and has broad-reaching programs. Global Oncology University has a fabulous foundation and network of support. Organizations like Rios Contra Cancer also have wide-reaching and huge volunteer databases to draw on. So I think maintaining the communication between all of the key groups is really key in ensuring that we're addressing all of the problems. So I love the idea that Global Oncology University is really looking at the foundational level learning. So that real, almost undergraduate physics core knowledge that successful and competent and safe medical physicists need to understand. And then you have programs that the IAEA are running, which are more in the behavioural domains of learning. So it's more around the practices and processes. So all of those things intricately linked together. So the online residency program that we run really is focused around entrustment and participants and what do you trust them to safely do. And we actually break that down into two different domains of learning. So we have behavioural and cognitive. So it's all lovely and good to teach someone how to do something, but it's also understanding the why and the what happens when things don't go the way they should, particularly in lower middle income countries where outside the box thinking has to happen on a day-to-day basis. So if you don't have that fundamental understanding of the physics concepts and processes that live at the very heart of it, practice will not be safe. You won't be making safe and good decisions for your patients. So I think all the different layers that all the different organisations are doing currently is starting to form that package that successful clinicians need globally. I think and I know everyone's working towards this, I think a lot more collaboration is probably key in that space.
So just a quick follow-up. So for your online residency program, how did you evaluate the residents to make sure that they were actually comprehending the courses, the experiences, and the lectures, everything that's involved with the residency program, that you knew that they were actually successful?
That's a great question. So we have key touch points with each of our residents. So we have a team of what we call periodic progress assessors. So they're an external trained group of people, and they will meet virtually with each of the residents over periods of time. So the first meeting with an external assessor and the resident occurs 6 months into their residency program. And we have a rubric of different levels of, again, behavioural and cognitive domains, and the expectations of where residents should be at particular times through the training. So we do touch base quite often, and for residents that are at risk of possibly not successfully completing the program or who are struggling, these particular touch points highlight those residents to us, and then we can provide them the extra support that they need to get through the program. So we've found that infinitely useful in making sure that residents are progressing through the program and getting the support they need to do so.
Okay, thank you. So Andrea, question for you. I know you gave some examples of AI and VR how they're transforming medical physics education. So how do you see these technologies playing a role in kind of on the ground training for like nurses, oncologists, therapists, physicists, kind of across the board?
Well, I think that that's a hard question to answer right now, because AI is so much in flux. If we think about what the potential for AI is, we envision it as a like an effort multiplier, something that makes or an effort easer, something that makes things easier for us to do. And we're not really at that stage right now. When we're using AI, we're bringing in additional tools. It's taking us sort of away from our patients in some ways to sort of interact with those tools. So we're at the infancy in that, but I mean, it's quite clear that AI is going to, revolutionize the way that we work. You can do things like using AI to validate reports, to do chart checks, to revise and supervise and evaluate treatment plans and things like that. So from a practical perspective, what we need to do is make sure that we train people so that they understand these AI tools, that they can work with these tools, and also to help in developing these tools, right? As if these tools are going to be helping me to do my work, then I need to be able to have input into those tools. So what you're seeing right now really is sort of the infancy of these things. So we're teaching students how to develop AI models through, in some cases, fairly, like rudimentary exercises, but things to get them into understanding this. I mean, the other thing you have to remember is a lot of these students, even though, they came out of undergrad, perhaps even just a few years ago, AI has changed so much in that time that they were not exposed to those. So, they didn't take courses in large language models. You know, that they're, the tools that are being used, PyTorch and things like this. When I, started teaching AI a few years ago, we were using Jupyter notebooks. Today, we're using something completely different. We're using Visual Studio Code with, like Python add-ons and Chat GPT to help us code. So it's a time of flux, and we just have to be very like we have to be willing to sort of adapt as we go along and to learn the best models. In terms of holographic imaging and things like that, you are seeing those coming into the hospital. So, for example, in our interventional radiology facilities, we are using holographic imaging, and we're doing holographic projection of CT and MR data onto the patient, so that the radiologist is getting real-time feedback and guidance of their interventional procedures through interaction with CT and MR data. So it's as if you can see a cross section of the patient as you're, threading a catheter in or something like that. So we're starting to see inroads in this space, and HoloLenses and things like that are becoming more common. I don't know if you have seen like the Apple goggles and things like that, the Apple glasses, and these things, the new Meta glasses, that just look like you're the sunglass version of what you're wearing right now. These are going to revolutionize the way we teach, because you'd have a much more interactive experience. I mean, think about what Claire is talking about. Imagine, that, the Meta glasses are $300, which is not cheap, but it's not the $3,000 that the Apple glasses were last year. Imagine that, Claire's residents could wear, Meta glasses as they walk into a clinic, and go in and do work on setting up to do dose depth curves on a Linac or something, and she can sort of sit there and say, no, you need to do this, you need to do that. I think it will lead to a much more interactive experience and enable a lot more sort of remote instruction.
Thank you. So, Mara, question for you. I left an easy question for you.
Oh, thanks.
If you could implement one major policy or program to improve global oncology workforce development, what would it be and why?
The question is to me,
Yeah.
right?
Yeah.
Okay. Actually, it's not an easy question, but we can start from what the agency is doing in that regard, maybe, and how we are trying to harmonize programs and have activities at a global level. And for instance, one of the latest initiatives of the IAA is the network of anchor centers, which was developed through the Rays of Hope initiative. And these are hubs that will be that are dedicated for education and training, mainly in all the regions of the world. We currently have 12 anchor centers, and we will have most likely more in the future. And with this anchor center, we are trying to have regional approach to training with all several professional organizations supporting us. And actually, through anchor centers, we will not only address education and training, but we will also work on innovation and research on education, for instance, and trying to really create a network of centers worldwide that we can use for training staff. So is it somehow answering your question, or can you repeat your question? Yes.
I guess it's probably one of these blue sky type questions. Like if you had one wish, and I said if you could implement one policy or something or one program that could improve the workforce, like what would it be? I guess that's the kind of question. Like what would be your wish if someone granted you one of this is what you could do to actually improve global oncology workforce development?
I think
and we can come back. Like I said, I gave you the easy question. So
no, I think that we have to start understanding why we have this lack of global workforce and how we can. For instance, if we look into medical physics, we have to start from the basics and having medical physicists being recognized as health professionals. So if we have to start with a policy, the policy should be that medical physicists should be recognized as health professionals worldwide. This is the basic to build up and then start on this. And then once this is recognized, we can work together on giving them access to the proper education and clinical training. So the other point is the lack of clinical training. Obviously, these innovative tools are essential, are fundamental, but we believe that the hands-on clinical training it's also fundamental for medical physicists, and this should also not. We should make this happen to all. Make sure that all medical physicists will have access to some sort of clinical training, hands-on clinical training in the clinic. So this maybe can be the two policies. I'm thinking about medical physicists because this is the reality I know best. But actually, this is the basics we should start with.
And so, go ahead, Andrew. You want to follow up?
Yes.
So I would follow up. think what Mauro said is really important, that we need to sort of deal with this more broadly and make this more ubiquitous. And that ties into something I had in one of my slides, which is the idea of having majors and minors in medical physics at an undergraduate level. So imagine you have someone taking computer science and they take either a minor in physics or a minor in medical physics, right? You have someone now who can come into the field that might not have otherwise been exposed to the field, who will bring new knowledge into the field. Will bring sort of the latest, AI methods. You asked about AI, right? And the fact is, most people in the audience probably did not receive any education in AI, or very little. They took one course in it. Imagine somebody who took 10 courses in it, and did a senior project in AI, worked on a large language model for a specific application. If they had had exposure to medical physics, then they would be doing a large language model research, or large language model experimentation, as it would help medical physics, hopefully. So I think moving the point in time where people are first introduced to medical physics earlier is really the key. And you see that, I know, Penn State University, which is one of the local universities to me and to Dr. Avery, they have an undergraduate degree in medical physics. And we've taken a number of their students, and they come in much better trained than, or prepared. Maybe that's a better word, because I don't think they're better trained, but they're better prepared for what they're going to see in medical physics. Mauro.
Yeah, I think that just for the sake of time, I wanted to go to some of the questions that we have in our Q&A, just so we can address some of those. So I know that someone had a question about what is Global Oncology University. So I put a link in the chat that will take you to the website so that you can know more about, in detail about Global Oncology University and some of the other initiatives that are happening there. There was also a question about explaining the hallmark of cancer. We probably don't have time to go through, in detail, but basically these are the things that the hallmarks of cancer is also things that enable the cells to grow and actually to evade tissues, and so again, this is probably not a subject we can explain in 10 minutes, but I did want to try to address some of those questions that it had. So we had another question about, it says, what is the IAEA's Rays of Hope initiative doing to train and other efforts by IAEA in training, leveraging AI and technology?
Actually, the Rays of Hope initiative is an initiative addressed to fill the gaps and try to improve the standards for access to radiotherapy and standards for particularly LMICs. What the IAEA is doing in the field of artificial intelligence, actually, we started a few years ago. This is through the Rays of Hope initiative, but not only addressing, addressing the needs of professionals working in AI, with AI, and in medical physics. We published a couple of years ago already, I think it was 2023, guidance on roles and responsibilities of medical physicists working in AI and education and training needs. And based on this, we started organizing training courses also for medical physicists. We believe that medical physicists should use, that are going to use AI, and AI is coming in the clinical practice, we know. They should not approach the use of AI as a black box, but they should have understanding of what's behind this and having an understanding on the principle. This is also to build up on what Andrew was saying. So we organized a regional training course at ICTP, and we are going to organize other courses in the near future. And we are going to finalize a publication on how to address all the steps that are needed in the use of AI as a medical device, from marketing, market research to procurement, technical specs, commissioning of these tools, quality assurance, down to the commissioning of these tools. So we are working actually on providing guidance for professionals on the use of the AI, because we recognize that AI is very important. And medical physicists are very important in the use of the AI because they speak both languages. They have a scientific knowledge, but they also understand the clinical language. So they are the perfect bridge between these two domains.
So Claire, there's a question for you. It says, will residency programs look different in the near future? That is, if AI can do a lot of things like segmentation, do residents need to spend years on this?
Oh, that's a really great question. And I guess any residency program or any training curriculum needs to keep pace with technology and current best practice in the clinical field. So yes, residency programs will look different in the near future. So for example, we've just done a curriculum review for our residency program, and AI is now one of the key components of learning, which didn't even exist in the program 5 years ago. So we are trying to keep up with those things. I think in terms of AI in the workplace and things like automatic segmentation and automatic planning and scripting, basically doing everything for you, there's sort of a two-level learning process in that. So it's understanding what that AI is doing and how to safely implement that in the clinic, because AI is very much a black box, particularly in those commercial products. You don't really know what it is they're doing, just what the end outcome is. So we need to learn how to evaluate those commercial products and implement them safely. But behind the ability to do that is, again, that fundamental understanding of what it is to do. You cannot evaluate whether automatic segmentation is good or bad if you don't know how to segment or contour those organs yourself. So there's that fundamental background learning that you need to have in order to assess the new technology that is coming in, particularly as the technology is getting more and more complex. So I think residency programs will still try and balance out the new and how to implement new technology with that foundational level knowledge that you need to do the latter safely. So to implement safely, you still need to have that foundational knowledge. So our programs will always have a core physics knowledge or clinical knowledge that you will need well into the future, regardless of what happens with technology. And then what we have is we have a special section in our residency about advanced technologies. And so they're things that pop in and out. So at the moment, AI is in there. We've got, in Australia, we don't have a proton unit at all. So that's in our advanced technologies. So we're incorporated into our curriculum because we see the need in the future, because we will have proton therapy in our country in the next few years. So it's trying to foresee what is coming and direct some learning towards that to be prepared for it when it arrives.
Great. There's a question from Andres Diaz. He says, how do we leverage new technologies to facilitate access to equitable, high-quality training without leaving institutions behind, given the rapid pace of technological advancements? It feels like technologies are coming in every year, and we're all scrambling to keep up with multiple fields of medicine. So anyone want to take that one?
I can give my opinion.
Sure.
There's two issues, I guess, in this. Yes, we have new technologies coming in all the time. Those new technologies come at a cost. And it's often the lower middle income countries that can't afford that cost. And so in lower middle income countries, you've got the biggest spectrum of technology that you will see. So, you'll have basic cobalt therapy units And then you will have also that AI and auto segmentation and all of the high tech things as well. So having to cover that broad spectrum because of the spectrum of equipment and technology that they have in different countries is a real challenge. So how do we leverage new technologies for training? I think, again, this is where virtual reality and augmented reality and AI systems will come into play. So there are certainly in the field already some virtual reality training systems. There's a company called Virtual who've been around since about 2009, and they have virtual reality systems and they update them as technology updates. So I remember in 2009 they started and they had, you know, basic Elector and Varian machine models, whereas now they've got they've introduced proton therapy as a virtual model as well. So it's trying to keep, I guess, that the AI and the learning technology up to date with the clinical technology at the same time. So it's a full-time job for people to try and incorporate both together in a system that will work on a global scale.
Thank you. So Andrew, it's a very interesting question. I think this is probably more towards you. It's about radiologists. Will we need radiologists in 10 years? And LMICs, do we need to train radiologists or just use AI?
Yeah, so that's the million-dollar question, right? Jeff Hinton at the University of Toronto was sort of famously quoted as saying about 10 years ago that we should stop training radiologists. We wouldn't need them in 5 years. Well, that time has come and gone. And the view that I prefer is the view that I'm blanking. Oh, Kurt Langlotz promotes at Stanford, which is that, you know, we will replace radiologists with radiologists who use AI. You know, I don't think we can completely eliminate the role of radiologists. It's clear that AI has you know, some role in radiology. For example, you know, there are efforts to have AI-enabled tuberculosis screening using radiography in Africa. So they have these. There's an organization that will take portable radiographic systems throughout Africa. They'll you know, go to a village. They will image you know, the population of the village, and those images get transferred by satellite back to, you know, a server in Europe that does diagnosis. But this is a very targeted task, right? There is something called the gamuts of radiology. And in fact, there's a great website that you would want to go to called the gamuts of radiology. And what this is it lists all the diseases that you could possibly imagine seeing in a chest x-ray, for example, or in a musculoskeletal x-ray, an abdominal x-ray, a mammogram even. You would think it's just breast cancer, but there are other diseases that are evident in mammograms. There's something like 250 diseases that can, you know, be easily diagnosed from chest radiography. So, you know, how do you implement that? Do you have to have 250 different AI algorithms? Do you have to have, you know, some generalized AI algorithm that can see all of these things? And then how do you convey those results? Who's going to talk to the clinician? Who's going to talk to the patient? So I really don't see AI replacing anyone. What I envision is AI making certain tasks sort of redundant or unnecessary by humans. You know, Claire talked about this, about segmentation. From a research perspective, segmentation is considered a solved problem. It's not completely true, but, you know, algorithms like Segment Anything and SAM2 and stuff like that, the medical SAM versions, they're really good. But as she pointed out, you still need someone to QC that. You still need someone to have that knowledge. You still need someone to be able to teach segmentation to the next generation. Because, you know, at some point, something may happen where SAM doesn't work with it, right? Or the system breaks in some way, and we need to be the overseers of that process, to the end. So no, we'll have radiologists. We're going to have radiation oncologists. Um, it's there will never, I do not think there will be a time in our lives where, we just say, computer, I don't feel well today. What's wrong with me? And it scans you and like Star Trek.
Yes. So I know we're coming close to the hour, but I just want to ask one last question. Maybe we can keep it short. So along the same lines of, will we need 10 years? Who will we need and what would they look like? What will the curriculum of the future look like? Not only for physicists, but just in general, for oncologists, for nurses, for therapists. How do you see it changing from the curriculum that we have now? I know IAEA has a dedicated curriculum that a lot of LMICs use. I know, Andrew, you have a curriculum that you use at Penn and Claire with your residency program. So maybe you can say just in a few minutes, like how would that curriculum change in the future from what we have now?
I can jump in.
Sure.
That's a really tough question to answer. I think, as I've said before, I think there will be parts of the curriculum that will never change because that is our fundamental understanding and our fundamental learning of whatever the process is we're learning. So whether you're a radiation oncologist and, it's the fundamental process of cancer and the interactions of radiation cancer cells and, clinical evidence-based practice, or physics, the fundamental interaction of physics with matter and radiation detection and all of those things they're not going to change. So there will always be that core curriculum that will stay. And I just don't see that ever changing. And then it's what we build around that in order to meet the changing technology. So some things will disappear and other things will come in. So at some point, conformal radiation therapy will no longer exist. Everything will be VMAT, IMRT, other methods will come in. So things will drop off as technology improves and replaces them, and then that becomes the global standard. So at the moment, the problem is the global standard is so wide. There is no global standardization, particularly in radiation oncology. And a lot of that is because of global technology differences. So, like I said before, you have countries that have basic cobalt units that can only treat square fields or rectangular fields. There's no beam shaping. There's no intensity modulation. So they're limited by what they can learn and what they should be learning based on the technology that they have. So really, what I would like to see in the future is global standardization, both in the technology space and also in the educational space. And then that will bring global standardization of patient care and patient treatment quality. That is the ultimate aim, is for every patient around the world to be getting the same level of care as any other patient, regardless of where you live. So that's the dream. I think, unfortunately, that's a long way from reality. And what will happen is curriculums will need to be developed that are sensitive to the requirements of that individual region. So, for example, the residency program in Australia is different to the residency program I'm building for Nigeria because the two regions have completely different needs because of their current technological differences. So at the moment, curriculums need to be specific to account for what you need in your space. But ultimately, I would love to see a global curriculum and global standard that everybody can adhere to.
Thank you, Claire. Andrew or Mauro, do you want a quick comment on that?
I'll jump in quickly if I could and let Mauro have the last answer because he's the IAEA. So I think to some degree, we just take advantage of all the things that are going on, internationally. So, really just sort of ride Moore's law. You know, the computational power that I could buy from NVIDIA today, you know, is expensive, but in a couple of years it will be cheap at that level, and that's going to really push things along. I haven't really talked about it, but I work extensively in South America, particularly in Brazil. I've had many graduate students in my lab from Brazil. One of the things that I've noticed from their education program, as Claire pointed out, is they have a stronger background in the fundamentals than the students I'm getting from American universities today. You know, they're better trained in terms of fundamental physics, fundamental math, fundamental computer science. Um, and so they're very strong students and a pleasure to work with. But the problems that we can solve together are different because they have resource limitations. But the things that they have most access to are, you know, sort of year or 2-year-old GPUs. And there's incredible things you can do with those in terms of simulations, in terms of modeling, in terms of AI. So they're really doing what I think is fairly cutting edge research. The other thing is these limitations to some regard require them to be more careful about how they program. You know, when you have a cluster of 1,000 computers, you don't need to make your code efficient. But when you have a cluster of one computer, you know, you really need to think about how you're doing that. And I think that we need to actually learn from that and go back to thinking about how to make medicine cheaper, more cost effective, because then that has a follow on throughout the world. If we can make medicine more cost effective, then it's easier to implement worldwide.
Thank you. Maura, last word before closing remarks.
Yes, quickly. I think, what do we see for the future? I think what we have to make sure is that professionals will still be trained on principles, because the fact that automation will increase doesn't mean that they need less background knowledge to make sure that technology will be used properly.
Thank you.
Mhm.
So,
Can I say one last thing? Never stop learning. Always keep reading your books. I'm reading quantum mechanics books right now from my undergrad because I've forgotten it. Never stop learning.
thank you. Yeah. So it's great discussion. So just as a wrap up from the discussion today, I know we have a couple of minutes. I just want to take a moment to thank our incredible panelists for sharing your insights and expertise. I think it's clear that, you know, transforming the oncology workforce is a big challenge, but I think it's an urgent need globally. So just a few takeaways that, you know, from today's discussion. I think education disparities remain a major hurdle, I think, in oncology workforce development, particularly in LMICs. That, you know, technology offers powerful solutions. We talk about AI, VR, holograms. They have the potential to revolutionize how we train the oncology workforce globally. Collaboration and innovative models are essential. I think that, you know, things like Global Oncology University and other international partnerships will play a crucial role in bridging many of the gaps today and things that will happen in the future. So this conversation doesn't end here. You know, I would invite all of you to continue these discussions at the upcoming Global Health Catalyst Summit. So where we would dive, you know, deeper into some of these questions and actually explore some collaboration. So finally, again, a huge thank you for all our participants for joining us today, and thank you for your questions. You know, we really appreciate, you know, your engagement around this, and we look forward to seeing you at our next webinar. So stay tuned for more details of upcoming topics. So thank you all, and have a wonderful day. Thank you.
Thanks all. Enjoy your weekend.
Thank you.
Thank you so much, Steve.